So just as a reminder, 6-1, 6-2, and the 6-3 homework, those two homeworks are due this Friday. We completed 6-1 and 6-2 last time. We'll do 6-3, and we'll actually get into a little bit of 7 this time. So trying to think of, yeah, I don't have anything really other than, yeah, don't forget about the homework, okay? All right. Well, let's get into 6-3. 6-3 is on the inverse trig function. So the inverse of our trig functions. So we have already, when we were dealing with solving right triangles, we've already used sine inverse on our calculator and cosine inverse on our calculator and tan inverse on our calculator, all right? So we used sine inverse of something, cosine inverse of something, tan inverse of something on our calculator. When solving right triangles. So when we're solving right triangles, we had sine of some angle is equal to a ratio, some other number, and then we could figure out what the angle is. Okay. So we should be fairly comfortable with putting those out there. Now, here's the deal, and this is basically all of what 6-3 is, okay? We have to create functions out of these. That means when we create functions out of these, we have to restrict our domain, okay? Or else they're not going to be functions. They're not going to be, not going to pass the vertical line test. Does that make sense? So when we use these, we need the right, I'll say correct, domain and range. And it turns out the domain and range for these are not going to be all the same, right? For your sine inverse, for your cosine inverse, for your tangent inverse, the domain and range are not the same. And we know that because if we look at a graph of just sine, for instance, so let's take a graph y equals sine x, pull this down. Notice while this is a function, because it passes the vertical line test, it's not 1-to-1 because it's not going to pass the horizontal line test. Okay. So as a function, sine, the inputs can go from negative infinity to positive infinity. But what we're going to do is we're going to restrict it to one period. Okay? One period. And so I have to pick a spot where, did I say one period? I should have said basically a half period. I apologize. I misspoke. I don't want to restrict it to one period. I want to restrict it to a half a period. So here's the deal. If I go from, let's do this. If I go from 0 to 2 pi, and I use that as my domain of sine, so my range of the inverse, then it's not going to work. I'm going to fail the vertical line test when I do inverse. Okay, follow that. So what I do, I have to pick a value that starts and that ends, where we get everything in the range of sine. So every number between -1 and 1 as the output, but where I don't have any repeated outputs. And so what we do is we restrict our sine to exactly what I just had there, from negative pi over 2 to positive pi over 2. Now, that's not the only choice I could have made. I could have started at pi over 2 and went to 3 pi over 2. I could have started at 3 pi over 2 and went to 5 pi over 2. But the reason I chose this one is for two reasons. One is that it goes through the origin. And the second one is that this matches up with what our calculator is going to give us when we type in inverse sine. I didn't have to worry about that when we were solving right triangles, because when we were solving right triangles, it was always going to be angles between 0 and 90. Does that make sense? 90 degrees. So all of our values went from 0 to pi over 2 in terms of radians, or 0 to 90 in terms of degrees. So I didn't have to worry about the domain and range too much. Now, if we have y equals cosine of x, if I try to go from negative pi over 2 to positive pi over 2, it's not going to work, right? I'm going to fail the horizontal line test. I need my cosine to be 1 to 1. So instead of going from negative pi over 2 to pi over 2, I'm going to go from 0 to pi. That makes sense. So I'll write this all on the board in a second. But you can see if I restrict the domain of cosine to 0 to pi, it's both a function and it's also 1 to 1. And the starting value gives me a y value of 1. The ending value gives me a y value of -1. tangent, basically with tangent, so that we get a one-to-one function with tangent, we're going to restrict its domain, and we're just going to restrict its domain to one of those. And again, I like the one that goes through the origin, both because it goes through the origin and also because that's what our calculator is going to do. And it turns out if you restrict the domain of tangent to negative pi over 2, to positive pi over 2, that gives you exactly a one-to-one function. All right. So all of this is just to say we have to define our sine, cosine, tangent on a specific domain in order for the inverse sine to work, inverse cosine to work, inverse tangent to work. And the inverse tangent, if my trig function is defined on a specific domain, then the inverse tangent is going to have range between negative pi over 2 and positive pi over 2. The inverse cosine is going to have range from 0 to pi. And the inverse sine is going to have range negative pi over 2 to positive pi over 2. Okay. And that's what we'll write on the board. Right? So when using inverse functions, we restrict domain of our trig functions and the range of the inverse trig functions will be restricted as well. I'll just put I'm going to get to why this is so important in a few examples here. Okay, but so let's take y equals sine of x. For y equals sine of x, the domain technically is all real numbers, usually, right? If we want inverses, if I want to have an inverse, my domain is going to be between negative pi over 2 and positive pi over 2. By the way, the range is like it's always been, y values, the outputs of sine are always between -1 and 1. So if I want to have a true inverse, if I want to make this a 1-to-1 function, I have to restrict the domain. And therefore, if I have an inverse trig function, f of x equals sine inverse of x. Obviously, this is defined where the domain is between -1 and 1. I can't get a sine value that's any bigger than 1 or any less than -1, right? And the output is going to be between -pi/2 and +pi/2. So if we want to have an inverse exist, this is kind of how we have to treat it. And the reason we had to do that was so that our sine function was 1-to-1. With cosine, for the inverse, if I want to have an inverse, domain has to be restricted between 0 and pi. And the range, well, again, cosine range is always going to be outputs between -1 and 1. Right? If we do what? F of x. If I let my cosine be restricted there, then I can find an inverse of cosine, and the inverse of cosine is going to have a domain between -1 and 1. And the range of cosine is going to be restricted to be between 0 and pi on the calculator. With tangent, if I want to have an inverse, I have to restrict my domain to -pi/2 to pi/2 so that my function is 1-to-1. By the way, the range goes from -infinity to +infinity. Right, goes all the way up, all the way down. I shouldn't put equal, but. And so on my calculator, I can plug in any number into the domain, or I can plug in any number into tangent inverse. But as far as the range goes, we need to expect to get out values between negative pi/2 and positive pi/2. Okay. So to have a true inverse, that's what I have to do on all of these. I have to restrict the domain of the trig function to get an inverse, and that means that the output of the inverse function is going to be restricted. And that's the important part. The important part is the output of the inverse function is going to be restricted to a certain range. Okay. And that is really, really important to know. So the range of the inverse function being restricted is an important thing to know. In general, we do not restrict the domain of our trig functions, right? Does that make sense? In general, we do not restrict the domain of our trig functions. But I'm saying if you want your trig function to have a true inverse, you have to restrict its domain, and that restricts the range of the inverse by necessity. All right. Now, just as a side note, a lot of times people will get confused by this notation. They'll think it means sine raised to the negative first power. That's not saying this is the inverse sine. And so there's another notation that people use for inverse sine called the arc sine. And you can do this with cosine and tangent as well. That means the same thing. So notationally, sine inverse of some value is equal to the arc sine of that same value. And again, we say arc sine, A-R-C. Or cosine inverse is equal to arc cosine of whatever the argument is. And the tangent as well is arc tan. And some people like to use this notation rather than this so that they don't think it's tangent raised to the negative 1 power, because that's not the same thing. Inverse tangent is not the same thing as tangent raised to the negative 1 power. Inverse tangent is the inverse of the tangent function. the inverse function of the tangent function. So if you see these things, arctan or inverse sine or whatever it happens to be, it's just inverse tan, inverse sine, whatever it happens to be. So let's do some calculations. Let's calculate sine inverse of √2/2. And we're going to do this in radians again. So make sure your calculator is in radians. I know in chapter 6.1 and 6.2 we were dealing with radians. But what was it? The last section in chapter 5 was right triangles, we dealt with degrees. But most of the time we're going to be dealing in radians here. So let's deal with radians. So make sure your calculator is set to radians. And sine inverse of √2/2. We could type this in to our calculator and get 0.7854 roughly. But let me explain why this needs to be pi/4. Okay. That is 0.7854. That's the decimal version of it, right? So we can type it in to get the rounded answer. But let me explain why I know, without even having to type it in, that the answer is pi/4. If I go back to the unit circle, on the unit circle, sine was how high on the unit circle it is. So if I have a point on the unit circle, remember that point is point cosine theta, comma, sine theta. Right? And at one point, we figured out, by at one point, I mean at one spot in chapter 5, we saw that √2/2, comma, √2/2 happened, that value, at angle pi/4. Remember doing that kind of tracing stuff? So since the y value of, so since I knew sine of pi/4 is √2/2. The inverse sine of √2/2 has to be pi/4. Now, here's why we have to concern ourselves so much with the domain and range, well, with the outputs specifically of sine, is that on the unit circle, there was another angle whose y value was root 2 over 2. And that was 3 pi over 4, right? We also knew that sine of 3 pi over 4 is also root 2 over 2. Why does this have to be pi over 4? And why can't this be 3 pi over 4? Well, because we all agreed that we're going to restrict the range between negative pi over 2 and positive pi over 2 on my sine inverse. So in other words, when you're dealing with sines, it's going to give inverse, it's going to give you angles over on the right-hand side of the circle. Does that make sense? It's going to give you angles on the right-hand side of the circle. And it's always that second coordinate of your point on the unit circle. That's what sine gives you, so there you go. All right, so this is why we have to be really careful about understanding what we're going to get out. Sine, I'm going to get angles on the right-hand side of the unit circle. For cosine, let's do cosine inverse of, let's do root 3 over 2. Actually, I'm going to reframe that. Let's say we want to write arc cosine of root 3 over 2. Is that different than what I just had? No. Inverse cosine, arc cosine, same thing. Oh, yeah, that's fine. I should have probably put it. I'll do that next. All right, so we're trying to remember what first coordinate gave me root 3 over 2. And by the way, that'd be comma 1/2. What first coordinate gave you that point? What that I said no, I misspoke. Not what first coordinate. If the first coordinate gave you that point, what angle am I looking for? Anybody know? Go.
Was it pi over 6?
Pi over 6. Yep. Pi over 6. So if you want the exact value, it's pi over 6. By the way, you can always check this on your calculator by doing inverse cosine of square root of 3 divided by 2. And then calculating pi over 6, just to make sure you got the same thing, right? Just to see that it is pi over 6. Sure enough, plug this in on your calculator using COS inverse. You get pi over 6. Let's do this. Let's say we want to do arc sine of negative 1/2. there's two places on the unit circle where I get -1/2 as my second coordinate. One of those places is here, where I get √3/2, comma, -1/2. And the other place, I'll draw in red, over here, where I get -√3/2, comma, -1/2. Okay with that? Because arc sine, or the inverse sine, generates out angles over here on the right-hand side of the unit circle, the one it's going to generate out is this one. And moreover, it's not going to call that angle 11π/6. It's going to call that angle -1π/6. That makes sense? Because the range is between -π/2 and +π/2. Okay, so it's going to call that angle -π/6. It's not going to call that angle 11π/6. I get it? So -π/6. And again, when in doubt, just type it in. Type in inverse sine, -1/2. And sure enough, I got -π/6, or the decimal version, I should say, of -π/6. Any questions about that? Now, that's exact. That's kind of thinking through it in the terms of the exact answers. Most of the time in this class, when we calculate, we might calculate inverse sine or inverse cosine of some ugly numbers. So if we said, let's calculate, for instance, inverse cosine of 0.82, or the arc cosine of -0.41, we're just going to type that into our calculator. This first one gives you roughly 0.61. Again, be careful that we're still in radian mode. And 0.61 radians is something in that first quadrant. Our cosine of -0.41 I got about 1.99 radians. And by the way, that's in the second quadrant. Does that make sense for cosine? Remember, sine is defined between -π/2 and +π/2, but we can't define cosine that same way because these two quadrants both have positive values for cosines. So when you define cosine inverse the range of inverse cosine is going to cover the top half of the circle. This gives me both positive and negative values for the first coordinate. And there you go. Let's do tangent. Take tan inverse of 1.73. And then take sine inverse of 1.73. On tan inverse, you should have gotten about 1.05. Again, that's first quadrant. Tangent, once again, is giving me values the same as sine, negative pi over 2 to pi over 2. So that's first quadrant, 1.05. 1.73, when I plug that into inverse sine, I should get an error on my calculator. And that has to do with the domain. The domain of inverse sine, remember, is between -1 and 1. So if you're above 1, like in this case, it's not going to work. You're saying, where on this unit circle do I get a second coordinate that's 1.73? You're saying, well, 1.73 is above the unit circle, right? So there's no way across the unit circle there. So the inverse sine has to take on values between -1 and 1. Inverse tangent can take on any values. But there you go. And by the way, these are all just radians. So we're saying if the output of cosine is 0.82, what radians? This is 0.61 radians. There's a couple of questions on the homework that say something like, well, if let me write this. If sine of an angle is -0.21 and the angle is between -pi/2 and pi/2. I try to make it so it matches our calculator. Then what does theta? How many radians? Put this in radians still. And all we need to do to find theta is say inverse sine of negative 0.21. That makes sense? So inverse sine can solve this equation as long as I restrict my output values, or excuse me, my values for theta. Oh, look at that, negative 0.21, huh? That usually doesn't happen. That's the rounded version. Does this make sense? So we can solve trig equations like that. Let's do another one. Let's do tangent. If tangent of theta is equal to 0.14, and my angle has to be between negative pi over 2 and positive pi over 2, what's the angle? I want you to find this on your own, and then do the same thing. We'll do this with cosine. If cosine of an angle is negative 0.80, and, well, for cosine, the output is going to be between negative, not negative, between 0 and pi. Then what is that in? Guess we can round it to a couple of decimal places. And again, we're in radians to do that. That was weird. Yeah, I picked twice in a row. We're giving the same, take them around in 2 places. It usually doesn't happen. All right. So for the first one, it turns out the tangent inverse of 0.14 is about 0.14. Rounded to 2 decimal places. That's weird that happened twice in a row. If I try to find my inverse cosine of negative 0.80, I get about 2.5. Okay? So we can use these to solve the equations as long as we all are aware that we've restricted our angle theta to a certain output. And the range of the inverse function is restricted. On sines and tangents, it's restricted to the right-hand side of the unit circle. On cosine, it's restricted to the top half of the unit circle. By the way, this does kind of make an interesting scenario when we calculate stuff. Trying to think of, let's do this. If I did something like, let's apply tangent to the tangent inverse of, I'm just gonna say 3.7. Know what's gonna happen here? These are inverse functions of each other, right? So you should get about 3.7. Now here's a weird thing. Do I want to confuse you yet? Not yet. That's it. All right, so let's do this. Let's do tangent inverse of tangent of 1.2. These are inverses, right? So you should think naturally I should get out a 1.2. And if you type it in this way, you do. You have a 1.2. Now here's the weird thing. I want you to type in inverse tangent of 3.7. You should have gotten about 0.56. So what the heck happened here? What the heck happened here? Let me talk about this one first, okay? This one is telling you what angle gives you a tangent of 3.7. And then, what would the tangent of that angle be? So we have some angle that gives us a tangent of 3.7. Let's say it's this angle here. Okay. You have sine theta as your second coordinate, cosine theta is your first coordinate. And you take the ratio, you get tangent. So we're saying, well, what angle gives me 3.7? Let's just say angle theta does, and then what's the tangent of that angle? Well, it's gotta be 3.7, right? There was another angle that gave me 3.7, and that other angle actually would have been down here. In this case. But I really don't have to worry about that other angle because an inverse tangent just gives me one of them, and then I take the tangent of that and I get 3.7 back. So let's talk about this one. This is saying, what is the tangent of angle 1.2? Now, angle 1.2 is somewhere in the first coordinate, the first quadrant. So if we hit this with tangent, and then we hit this with inverse tangent, we stay in the first quadrant. Because inverse tangent outputs are either in the fourth quadrant or in the first quadrant. So if we're in the first quadrant, we can hit tangent and tan inverse, and we're gonna stay in the first quadrant the whole time. That makes sense? That's different over here. 3.7 is an angle in the third. No, 3.7. Yeah, it's an angle in the third. Quad. That makes sense. Third quad. Well, tangent is either going to be, let me rephrase this. Inverse tangent is going to have outputs that are either in the fourth or the first. So what we're asking essentially is if we start with this angle, angle 3.7, what's the angle in the first or fourth quadrant that has the same tangent as that 3.7? And with that being a ratio, what you do is you draw a line straight across and you get whatever this angle is, which is about 0.56. In fact, if you wanted to calculate it exactly, notice these things have to have some relationship between going across, making a straight line. So there's actually, if you take 3.7 minus pi, you're gonna get that exact same number we just got. But the key thing there is that this starts in a quadrant for which inverse tangent does not spit out a value. This won't, 3.7 is in quadrant 3, and inverse tangent is only going to spit out angles in the first and fourth quadrant. And in this case, it had to spit out an angle in the first quadrant because of the relationships between tangents. Does that make sense? So that's kind of why most of the time you get the same number. But there are these weird cases where you input something into tangent, which is not in the first or fourth quadrant. So when you hit it with an inverse tangent, it's going to spit out a different number because that inverse tangent only spits out numbers in the first or fourth quadrant. And the same is true with cosine. So if I said, we're still calculating let's calculate cosine inverse of cosine 2.8. Two point eight is in quadrant 2. Cosine inverse will generate out a quadrant 2 value, right? And so I should, without even typing into my calculator, I should expect to get 2.8. Because 2.8 radians is where cosine inverse is fine. That makes sense? But if I take cosine inverse of cosine of negative 0.4, negative 0.4 radians is in quadrant 4, puts us into quadrant 4. The cosine inverse is going to either put us in quadrant 1 or 2. And by the way, for tangent, it has to be the same ratio, so it's going to put you in the diagonal quadrant. For cosine, it needs to be the same first coordinate. So cosine should put me here. That makes sense? So it should give me whatever angle that is. Should have the same value in the first coordinate there. So I'm guessing it's going to be a positive 0.4. Let's check it out. Sure enough, we get a positive 0.4. Everybody okay with that? Interestingly enough, because sine inverse gives me values out which are in coordinate 4, if I do the exact same thing, sine of negative 0.4, and then apply the sine inverse to that, I'm going to get a negative 0.4. Because this is where sine is. I should say where inverse sine has its range values. Okay, so it's all depending on the range of these inverse functions. That's all I'm trying to get at. Okay. Lastly, I want to point out these inverse trig functions I've been doing with cosine, sine, and tangent. Okay. You could do inverse trig functions with cotangent, secant, and cosecant. All right. It all does the same thing. We have to worry about the domains and the ranges. But if we restrict the domain and range of, if we restrict the domain and range of all these inverse functions, what we've done is we've created nice one-to-one functions. So that we can have inverses. And moreover, if we want to talk about evens and odds and all that kind of stuff, thought I was sharing. No. We want to talk about even and odd. Well, here's tangent restricted notice that my tangent function is not only a nice tangent inverse is not only one-to-one, but also since the tangent function was an odd function, we calculated that last time, right? Tangent was odd. Notice tangent inverse is also odd. It's symmetric about the origin. Okay. Do you remember what sine was? Was sine even or odd?
Wasn't sine odd?
Sine was odd and cosine was even, right? So sine was odd and cosine was even. So watch what happens when we plug in inverse sine. Well, that's going to be an odd function as well on its domain, right? For its domain and range, it's an odd function. And then if you deal with cosine inverse, what's that? Is that even? Not even, is it? Turns out cosine inverse is not even because even means symmetric about the y-axis, which would make it not one-to-one. Does that make sense? Go back to cosine with unrestricted domain. This is even. Even graphically means symmetric about the y-axis. But we have to restrict the domain And if we force it, read that up, I shouldn't have done the whole thing, but. If we force it to be between 0 and pi, the domain of cosine, all of a sudden it's not symmetric about the y-axis anymore. See that? So cosine was even with an unrestricted domain. That means, but with a restricted domain, it's not even anymore. That means cosine inverse is also not even. We follow that? Because we have restricted range here. So because we restricted it, cosine inverse is not even, but sine inverse is still odd. So odd things basically stay odd, but even things don't. When you try to take the inverse, we have to restrict the domain. That's basically it. So there's some weird things with cosines and sines and the inverse functions, okay? And those weird things just have to do with the restriction of how the domain of the trig functions go or the range of your inverse trig functions are. Okay? So that we actually have true functions, true one-to-one functions. All right, everybody all set? Everybody okay with that? Now, I'm going to move on to chapter 7. We're done. That's all you need to know for chapter 6. And we're going to move on to chapter 7. Chapter 7 is all on trig identities. So we're going to have lots and lots of trig identities. And sometimes people get flustered in chapter 7 because of the types of questions that we ask aren't necessarily a one process oriented, like you do step 1 and then you do step 2 and then you do step 3. In chapter 7, it's going to be a lot of, well, this big trig expression is the same as this other trig expression. Or is it not? And to try to prove that those two trig expressions are equal, or that those two trig expressions are different, there might be a lot of different paths to get there. And there's going to be some paths that are shorter than others. And that's what we're going to do. In chapter 7, we're going to either verify the identity or determine an identity, which means we're going to see which big trig expression is equal to this other trig expression or vice versa. Okay. We're going to see a lot of different ways a trig expression can be written, in other words. So let's start with some identities we've all seen. And this is what chapter 7, section 1 is about. So some basic identities that we all know. One is that how do I say? We'll call these the basic trig functions. relationships. So we saw, for instance, that tangent of theta is sine of theta divided by cosine of theta. That was how the relationships between trig functions are. These are the basic trig function relationships. We also know that cotangent of theta is the reciprocal of that. We also know that cotangent of theta, since it's the reciprocal of tangent, we could have also written cotangent of theta is 1 over tangent of theta. You could have also written tangent of theta is 1 over cotangent of theta, right? Secant of theta is 1 over cosine of theta. Another basic relationship that we've already seen. We've seen cosecant is 1 over sine. All right. Those are our basic, straightforward basic trig function relationships. Okay. Now, before I move on, let me also talk about negative inputs. Now, you can do this all with cosine and sine if you want. But since sine is an odd function, when we have the domain negative infinity to positive infinity, sine's odd. Even when we restrict our domain from negative pi over 2 to pi over 2, that's odd as well. We get that. If you plug in a negative, you get out the negative of what you get when you plug in a positive. Cosine is an even function on its domain, from negative infinity to infinity. So if you plug in a negative into cosine, you get the same thing out as if you plugged in a positive angle, whatever the angle happens to be. So these are all things we've seen before, right? These are all identities that we've seen before. Most of these, I think all of these came out of chapter 5. Although we did the even odd thing in chapter 6. So once we have these, then what we can do is we can ask things like this. What trig function is equal to the following expression? Let's take cotangent of theta divided by cosecant of theta. And then we'll do another one. Let's do what trig function is equal to, I'll do cotangent again, but this time I'll divide by cosine. Let's divide by cosine of negative theta. The positive theta. So here's what you do on problems like these. We turn back to those basic identities. And we rewrite cotangent, cosecant in terms of those basic identities. Cotangent is cosine divided by sine. Cosecant is 1 over sine. Now, some people right now can just say, oh, we have a sine in the denominator, sine in the denominator, so they're both going to cancel out. So they'll just cancel out the two sines. You can see that, since they're both in the denominator. The reason why they cancel out is because of this. Dividing by a fraction is like multiplying by the reciprocal of that fraction. And so other people don't like to cancel out denominators, or they accidentally get that confused. And they'll say, well, let's multiply by the reciprocal, then do our canceling out. So if I multiply by the reciprocal, I can see that the sign in the denominator and the sign in the numerator are going to cancel each other out. And I end up figuring out that if you take cotangent and you divide by cosecant, what you get is cosine of theta. So what trig function is this equal to? This is equal to cosine of theta. All right, let's check out this one. Cotangent over cosine. So I'm going to write cotangent as cosine over sine, and then I'm going to divide by cosine. Now, once again, some people will cancel the cosines right now because this cosine's in the numerator and that cosine's in the numerator.
Don't forget the negative.
Of negative, thank you. Oh, no, I did forget the negative on purpose, I'm sorry.
Oh.
I screwed that up. So I didn't mention this, but that's why I'm doing it. Sorry, so this is cosine of negative theta. Cosine of negative theta is the same thing as cosine of positive theta by our negative identities. I forgot to mention that. Okay. So cosine tangent is this. I use my negative identities for cosines and sines to get this. I did kind of apply two identities at the same time. Now at this point, if people want to cancel out the cosines, they can. You have to be really careful about that. Or you can do kind of the same thing I did over here. If I take cosine of theta divided by sine of theta, dividing by cosine, that's like dividing by cosine over 1, would be like multiplying by 1 over cosine. And then my cosines cancel out. And I get 1 over sine. 1 over sine is cosecant. So that tells me if I take the cotangent of theta and divide by cosine of negative theta, I get cosecant of theta. Is that all right? So we can use basic identities to manipulate, cancel out, do all kinds of other stuff. Now, these ones are fairly straightforward in terms of kind of the path that's laid out. I rewrite things into sines and cosines and then do some algebraic techniques to cancel out anything that's alike. But they're not always going to be as straightforward. Okay. And a lot of times, instead of saying what trig function is equal to this, what it'll say is something like, is this true or false? Is this statement true or false? So let's do a couple of those examples. So is this statement true or false? And when I say true or false, we're going to always assume for all angles, theta, or all x's, or all whatever the variable happens to be. Okay. So if I take tangent of, I'll use x as my variable instead of theta for this example. If I do tangent of negative x, and I multiply times cosecant of negative x, I end up with a secant, I'll say of negative x too. True or false? Now, in a case like this, there's a couple of different approaches. And that's why some people have difficulty with this. I like the approach of we're gonna assume it's equal until I can show it's false. So what I'm gonna do is I'm gonna sort of simplify both sides and I'll keep the equal sign there, right? So assume this is true for right now. If this is true, then that means, let's rewrite tangent as sine negative x over cosine negative x. Let's rewrite cosecant as 1 over sine negative x. And I'll also rewrite secant here of negative x as 1 over cosine of negative x. And then I'm gonna cancel out things if I want to. I could pull out the negative sign, but since I already have sine of negative x and sine of negative x, might as well cancel those out right now. Right now I have 1 over cosine of negative x is equal to 1 over cosine of negative x. If you want to say, oh, cosine of negative x is the same thing as cosine of positive x, you can. But that's kind of an unnecessary step. We can kind of see that this has to be true no matter what value of x I have, right? So that means since this one was equivalent to this one, and this one is equivalent to this one, this is a true statement. Now, I do want to put a little asterisk on all of these. And all of these will have this same asterisk. This is a true statement for values in the domain. Okay? There are certain values that you can't plug in to tangent, and there's certain values that you can't plug in to secant, right? Because of the restrictions on the domain. We don't want to have zeros in the denominators. So, for instance, pi is not in the domain here. Because pi, when I plug that in to sine, that would give me a 0 in this denominator. You can't plug in pi here. Does that make sense? You can't plug in pi here. Or assuming not pi. So you can't get zeros in the denominator. All I'm trying to get at. Can't plug in pi over 2. Because you get a 0 in the denominator here. So there are values for where it's undefined, but on values in the domain, it's true. And that's why, don't worry too much about, we're not going to do that. We're not going to say, oh, actually, this is not true when x is pi. Because one side doesn't exist and one side does. We're not going to say, oh, this is not true when x is pi over 2. We're just going to say, yep, this is a true statement as long as the values in the domain make sense. Right? And that's what we're going to do for every single problem. We're going to say, is it true or false for the values, the angles, the measurements in the domain that we're working on. Okay. So it's stuff like that. So a lot of true, false questions, where is this equation true or false? There's some questions where it'll say, here's a big expression, simplify it. What trig function does it equal to? And you'll have to choose the trig function. And it might be, there'll be a list of trig functions. You have to pick out, well, is it cosine or sine or negative cosine or negative sine or so on and so forth. Does that make sense? So, those are the basic identities of the trig functions, the 6 trig functions and how they relate. Also in 7.1, what they call a basic identity is what we call the Pythagorean identity. And we mentioned this earlier because every point on the unit circle is cosine theta comma sine theta. That means when you square them and add them up, they have to be distance 1 from the center, which is the origin, right? So when you take cosine squared plus sine squared, you have to get 1. Because that's the radius of the unit circle. So the Pythagorean identity says if you take cosine squared of theta plus sine squared of theta, you have to get 1 no matter what the theta is. Now, 2 other Pythagorean identities happen because of our basic identities thrown into this one. Okay? I'll do this off to the side, but it turns out this is just an arrow. That Pythagorean identity leads to this one. 1 plus tangent squared of theta is equal to secant squared of theta. That's another Pythagorean identity. And it comes straight from this. Another Pythagorean identity is that cotangent squared of theta plus 1 is equal to cosecant squared of theta. So tangent and secant are related with this Pythagorean identity, and cosecant and cotangent are related with the Pythagorean identity. I don't think I showed you. Have I shown how I got this in this yet earlier in the semester? I don't think so. I don't think that came up in chapter 5. Not yet, anyways. So this is our base Pythagorean identity. This is the one that everybody everybody in mathematics would tell you is Pythagorean identity. This is the one people have memorized. These two people generally don't have memorized. Here's why. Here's where the second Pythagorean identity comes from. So this one. Okay. We saw that the first Pythagorean identity is just a result of the unit circle. That a point on the unit circle is distance 1 away from the origin. So radius 1, so you square the x, square the first coordinate, plus square the second coordinate, you have to get 1, add 1. But once we know that, then what I do is I throw in my basic understanding of trig functions to this equation. So I take the basic identities that I know and I apply them to this equation after I divide both sides by cosine squared of theta. So I take my basic Pythagorean identity and I divide both sides by cosine squared. If I take cosine squared and divide it by cosine squared, and then I'll take sine squared and divide that by cosine squared. And then I take 1 divided by cosine squared. So dividing both sides by cosine squared gives me this. Cosine squared divided by cosine squared, that just gives me a 1. If I took 1 sine over cosine, that would give me a tangent. But if I take sine squared over cosine squared, that gives me tangent squared. Okay with that? Sine over cosine is tangent. So sine squared over cosine squared is tangent squared. 1 over cosine, we know, is secant. So 1 over cosine squared, it's like 1 squared over cosine squared, is secant squared. That makes sense? And that's exactly what this identity is. 1 plus tangent squared is secant squared. So all this identity is, the second Pythagorean identity, it's just my original Pythagorean identity divided by cosine squared on both sides. What do you think I do to get this identity?
Divided by sine.
Divided by sine squared, exactly. So that's exactly right. If you did the exact same thing, but instead of dividing by cosine squared, u divided by sine squared. You have to write this down if you don't want. Just gonna show it to you. The first piece becomes cotangent squared of theta. Sine squared over sine squared is 1. 1 over sine is cosecant, so 1 over sine squared is cosecant squared. So you end up with 3 different Pythagorean identities, but they're actually just all derived from this one, that first one. So let me give you an example maybe of how you would use this, or how you would use these. I'm just gonna say, let's find out what trig function is the following expression. Let's take cosine squared minus 1 divided by tangent. So here's the deal. Cosine squared minus 1. I see this cosine squared, and I say, well, is there any way to, get rid of it through simple cancellation? And not really in this case, because we have this minus 1 as a sticky point. I try to get rid of cosine through simple cancellation. I can't do that right here. So I look at my Pythagorean identities. There's one that involves cosine squared. And you have a couple of choices, but they all deal with, I need to manipulate this. If I want to, off to the side, I'm going to manipulate this. I can subtract sine squared from each side. And I would get cosine squared is equal to 1 minus sine squared. Now I have, again, I have a couple of options. If I want to, at this point, I can do a substitution for cosine squared. That's what I'll do right now. Okay. So at this point, I'm going to do a substitution of cosine squared. I'm going to replace cosine squared with 1 minus sine squared. One minus sine squared minus 1. This one and this one will cancel each other out. And I'll just be left with negative sine squared on top. Now, before I go any further, I do want to mention I could have done another substitution in this case. I could have, if I wanted to, had also subtracted the 1 here and then said cosine squared of theta minus 1 is equal to sine squared, negative sine squared theta. So I could have done that and then replaced the cosine squared minus 1 with the negative sine squared theta. That would have saved me a step over here, but it would have added a step over here. So it's kind of what my builder says, a 6 in one hand, half dozen in the other, right? Kind of the same difference either way you do it. You either do one extra step over there, and you can skip a step over here, or you do one less step over there, you add another step over here. So. Yeah. Friend of mine who builds houses says that, so that's 6 in one hand, half dozen in the other. About the same thing, right? Okay, so now we're kind of back where we were at the beginning of section 7.1, where now we can throw in some identities and manipulate. Oops. So we have negative sine squared, and I'm going to write that tangent as sine divided by cosine. And then now I have to erase some of this work over here because I don't have room on the board. I could have wrote over there, but I probably should have moved my scratch work off to the side further. But anyways, so this is equal to negative sine squared. And then I'll multiply by the reciprocal. So multiply by cosine over sine. Now, one of the sines is going to cancel out. In the numerator with the sign in the denominator. And so I don't get a single trig function in this case, do I? In this case, the simplest thing this goes down to is negative sine times cosine. So You may say, well, what's this look like in Moodle, or what kind of thing, what's it gonna look like in Moodle? Let's actually go to the Moodle homework, and I'll kind of show you what things you should expect. How Moodle is gonna ask a question like that, all right? So first off, you can see this says, question 1, determine if the identity is true or false for all angles in the domain. That's the type we were doing earlier, right? We have an equation, we just simplify and manipulate. You assume it's true, and then you just keep going down and down and down until you can see it's for sure true in the domain, or for sure false in the domain. Again, this says for all angles in the domain, ignore, for angles not in the domain. This is again true, false, determine if things are true, false. So we could ask the question that way. You could say, for instance, is cosine squared minus 1 over tangent equal to negative sine times cosine? Something like that. That's kind of what this is doing, almost. It also could say, here's a list of 5 expressions. Or we have the none of the above options. Here's an expression. What's it equal to? Let's say we just did our example that was on the board, and we simplified that down to negative sine times cosine. And we said, well, it simplifies down to negative sine multiplied times cosine. That's not A, not B, not C, not D, not E. So we'd have to pick F, none of the above. Okay. Now, if negative sine times cosine was on here, then we obviously just use that letter. But this is just a multiple choice kind of thing. Pick one of them two. I don't know if that's C, don't get me wrong. And this is the same thing, multiple choice. When I say, what trig function is it equal to? Well, here's a list of trig functions, or E. That's kind of what we're doing. So we simplify it till it's really, really in the shortest form we can. And then we pick one out, or if it doesn't exist in that list, we say none of the above. Is that right? So it's either going to be kind of a multiple choice matching or a true false scenario. Okay. Any questions about that? You're never going to have to type in, what's the simplest trig function, and you have to type it in. That's not something that I do. Because a lot of times, there might be multiple ways of writing this, and multiple simple ways of writing this. Okay. Any questions about that? Kind of like how Moodle's going to ask those questions. Yeah. Not too bad. Now, there's a lot of different options when you're applying these identities, and that's kind of where it gets tricky. People will look at this and say, I don't know where to start. Well, do you start with rewriting tangent, or do you start with manipulating cosine squared with the Pythagorean identity? And in this case, manipulating cosine squared gave us the probably better option. Okay. That might not always give us the better option, but in this case it did. And so we're gonna be using those types of things. Let's do another. And I'm just gonna say simplify on this one. Let's take cosine theta plus sine theta and square it. There's actually a very similar one on the homework, but. Well, that means I'm gonna take cosine theta plus sine theta and multiply it times itself. Cosine times cosine is cosine squared. Cosine times sine is just that, cosine times sine. Now I have sine times cosine. And then we have sine times sine. So sine squared. So I have 4 terms when I multiply that out. Hopefully we can see that cosine times sine is the same thing as sine times cosine. Order doesn't matter here. So I'm going to combine those, and I'm going to combine those and put these in the front. Okay, so I'm going to say 2 times cosine theta sine theta. And then I'm going to take cosine squared and sine squared. And I'm going to kind of put those next to each other. Now it's fairly obvious why I'm doing that. I'm doing that because cosine squared plus sine squared in art is a Pythagorean identity, which is equal to 1. Right? So this whole thing, cosine squared plus sine squared, can get replaced with the number 1. So we have 2 cosine theta times sine theta plus 1. We probably cannot get simpler than that, so I'll just leave it at that. And so what we're trying to get down to is basically there's a lot of different algebraic manipulations that we should know and remember how to do. We should remember how to do something like this, which is essentially just squaring a binomial. There's been a number of times where I have divided by a fraction. We should know that that's multiplying by the reciprocal of the fraction. Right? So we have to dust off all of our, algebra skills and apply them in these trig contexts. Right? In the context of these trig functions. And that's what we do. Any questions about this kind of process? I don't want to right now give you too much stuff as far as like too many examples that could be overwhelming, but there are a lot of examples on the homework for 7.1, 7.2 that you can try. So there's a lot of different little algebraic techniques that you apply. Trying to think if, nothing too interesting. Let me do one more algebraic technique that we haven't done yet, or at least I haven't done yet on the board, in the context of trig functions. Okay. Oh, shoot. No, I don't want to do that. Crap. Let's take secant squared of theta. No, it's going to be something different, wasn't it? I don't know. Let's try this. No, my example got ruined because I thought I had it in my head and I didn't have the example in my head. I'm sorry. I should look back at what I did the other day, but I forgot it. Shoot. Let's do want to do, sorry. Let's do this. I'll just do normal cosine. I was trying to do something too fancy. And I just want to do this technique. Just wanted to give you the technique. Not too fancy. Okay. So let's say I want to simplify this. Cosine divided by 1 minus secant. Notice this is not 1 minus secant squared. Right? Be nice if it was, wasn't it? Wouldn't it? So here's the technique. Let's say I want this denominator to be a single trig function. Off to the side, I remember that if I there's some relationship between secant squared and tangent, which is my Pythagorean identity, with secants and tangents. I have 1 minus secant squared, so that's what I'll do. I'll subtract secant squared. And then I'll subtract tangent squared from both sides. Is that okay? So it'd be really nice if I had 1 minus secant squared. Because then I can replace it with a tangent squared. Instead, this is probably not gonna work out as well as I had hoped, but gives me the technique. So how do I create if I have 1 minus secant on bottom? Just remember how to create 1 minus secant squared? Well, this is a difference of squares. So if I take the square root of 1, I get 1. If I take the square root of secant squared, I get secant, right? And if you remember, back in some algebra, just like when we have complex conjugates, or conjugates with square roots, when we tried to like rationalize our denominator, or when we tried to get a real number in our denominator, we can do this. We can multiply by 1 plus secant on both the top and bottom. There's a technique that we can do. By the way, let me take a second. There you go. So cosine times 1 plus secant divided by 1 minus secant squared. Does everybody understand why you get 1 minus secant squared? It's just like multiplying polynomials like the last problem we did. But when you look at the middle terms, you get 1, then you get 1 times secant, that's positive secant. Then you get negative secant times 1, that's a negative secant. And then you get minus secant times secant, so you get minus secant squared. So these two middle terms cancel each other out, right? That's why this technique is nice, because the middle terms cancel each other out when you multiply like you're multiplying polynomials, right? First term multiplies through, second term multiplies through. The middle terms cancel out. And then we're off to the races. Now, I want to, again, it's one of those things, whichever you want to choose first, I'm going to replace the 1 minus secant squared with negative tangent squared. When I do that, I'm also going to do another step. I'm going to write it this way. I'm gonna write it as cosine theta times 1 plus, instead of secant, I'm gonna write 1 over cosine. Because when I multiply cosine through, cosine times secant should give me 1. So that's just a way to see that's gonna happen. All right. So now when I distribute, I get cosine theta plus 1 divided by negative tangent squared of theta. Again, it's not a nice thing, is it? That's okay. Okay. Let me rewrite this. Cosine of theta over negative tangent squared. So the reason I like writing it this way, sorry, this whole process is just so I can do this. Now I have one expression on the bottom, and now I can divide anything on top by that one expression on the bottom. Right? So cosine theta can get divided by negative tangent squared. That's not gonna help me a whole lot. 1 can get divided by negative tangent squared. Now I'm using minus. Okay. This first fraction, cosine divided by negative sine squared divided by cosine squared, I'd have to multiply by the reciprocal. And if I multiply by the reciprocal, I'm going to get cosine to the third power in the numerator and sine to the second power in the denominator with a negative somewhere. Everybody okay with that? Kind of did that all at one time. Hopefully that's not a big deal. And then that second expression, 1 over tangent squared. Well, if the reciprocal of tangent is cotangent, then the reciprocal of tangent squared is cotangent squared. So I'll write that as minus cotangent squared. Okay. So there you go. Now that's about all I can do. I can't really go too much further from there without, rewriting, and I guess I could rewrite cotangent squared if I wanted to. What's cotangent? Cotangent, sine over sine, right? So if I wanted to, if you wanted to create it back into one fraction, you could do that. You guys know what I mean by that? If I wanted to create it back in one fraction, I know I'm a little bit over time yet, but so if you wanted to, it's negative cotangent no, not cotangent, cosine cubed minus cosine squared all divided by sine squared. All right. Everybody follow kind of what I'm doing there? I'm just going through a bunch of different identity properties and rewriting this thing in different ways, essentially. Right? And you can probably keep going if you'd like to. I'm not going to. I'm going to stop there. But you can see you get all kinds of good hot messes, right? Does that make sense? So having the ability to do some of those algebraic things is all I'm trying to get at, okay? So things like multiplying so that I get a difference of squares. That's like multiplying conjugates. Things like having common denominators or writing with common denominators and then combining the fractions. Things like that, okay? So we're done with what I was gonna do for 7 and 1. Or actually one more, this is an example that I wasn't planning on doing, but so we're done with 7-1. Next time we'll start off with 7-2, okay? All right, I'll see you next time.